And this question, it is given that a tank full of water has a small hole at its bottom. If 1/4 of the tank is emptied in T1 seconds and the remaining 3/4 of the tank is emptied in T2 seconds, then the ratio of T1 by T2 is. Just try to understand this question. So in this question it is given that there is a tank over here. Okay, a tank full of water. So assume that tank is completely filled with water up to some particular height. Let's say that is equal to h. Now we are making a small hole over here. Let's say we are making a small hole at its bottom. So let's say over here we are making a small hole. So what will happen? Water is going to come out with some velocity v, and we know the velocity of water is going to be root of 2 into g into h. Depends upon the height of liquid column over here. Okay. Now if 1/4 of the tank is emptied in a time t1, that means now its level of liquid is going to decrease with respect to time. As the water is coming out, the level of liquid is going to decrease. So with respect to time, as assume that the level is going to decrease, and after some times, let's say the liquid level is changes to a value that is equal to 1/4 of its tank, then means its height becomes equal to h divided by 4 if the total height is equal to h, and time taken for that is given as nothing but a t. So let's see how to find out what about the value of time taken for this empty this tank. So consider that at an intermediate situation, we'll assume that the height of liquid column above this one is y, and y is not a constant because with respect to time the value of y is going to decrease. As the liquid is coming out, y is going to decrease. So at this instant we can write the velocity of liquid which is coming out will be equal to root of 2 into g into y, and take it as area of this container is equal to nothing but capital letter A, and the area of small hole that we are made over here is taken as small letter a. Now we are going to apply Bernoulli's theorem between this point 1 and with the point 2, which is outside, and point 1 is on the surface of liquid. So according to first, let's say we go for this continuity equation. So according to continuity equation, we can write it as area into, assume that the topmost layer of liquid is going to down with the velocity or coming down with the velocity, take it as v1, and the liquid is coming out is nothing but v2. So we can write a into v1 should be equal to, like a1 v1 is equal to a2 v2, that is small letter a into v2. So we can write a into this v1 is representing the rate at which the value of velocity with the value of y is changing. So v1 can be written as something but dy divided by dt, rate of change of y, is equal to area into v2. v2 we can take it as a root of 2 into g into y. So we can write the value of dy as equal to small letter a divided by capital letter A divided by 2 root of 2g. All these things are, you can observe that all these things are constant. And one variable term I'm just writing over here, that is y is a variable, and the another variable I'm just writing over here, that is dt. Now we can integrate on both the sides. So if you are integrating on both the sides, what we'll get is this y root of y can be written as y raised to 1 by 2. When I'm just writing on the upper side, it's going to be our numerator, it's going to be y raised to minus 2. So we can write it as nothing but y raised to minus 2 into dy, integration of this is equal to integration of small letter a divided by capital letter A into root of 2g, all these things are constant, into the value of dt. Now just consider that it's like height is changed from a value h. So initial the value of y is nothing but this here. One we can just remember one more thing is that the value of its like height is going to decrease with respect to time. It's not like it is going to increase. So the value of dy over here is a negative value, so I'm just putting a negative value over here because with respect to time you might be observed that this y is going to decrease. It's not like the value of y is going to increase. So we can write this is equal to y and we can put the limit of y, means initially the value of y was nothing but h. Now it's changed to some other value. Let's say after some times the value of height becomes equal to, take it as y, or we are going to find out what about the value of time taken to change its height from h to h1. So I'm just putting the value of this as height is changed from h to h1. So you can write minus of, if I'm going for integration of y raised to minus 2, it is y raised to minus 2 plus 1, that is y raised to plus 1 by 2, and divided by 1 by 2. And now we can put the limit. Initial height was h, and now we are assuming that changed to a height h1 is equal to a divided by a, and root of 2g etc. are constant. Integration of dt is t, and time is changing from 0 to t. Our aim is to find out what about the value of time taken by this situation to change its level of liquid from h to h1. So we can write this is equal to like a root of like 2 into root of y, and the limit for y is changing from or minus of this value, and the value of this is changing from h to h1 is equal to, we can take it as a divided by a into root of 2g into t. So we can just put the value of limit over here, that is 2 into root of higher limit, we can put it as root of h1, minus root of lower limit, we can put it as root of h, is equal to a divided by a into root of 2g into t. Now if I'm just taking this root negative sign inside, so we can write this as 2 into like a root of h minus a root of h1, and we can put the value of constants over here like a and small letter a root of g will be the value of time. So by using this equation we can find out what about the value of time taken to change its height from initial value h to a final value, take it as h1. Now if you want to find out the value of time taken to empty the tank, then we'll put the limit from h to 0. So the value of h1 becomes equal to 0. h1 is a minimum as the height at the second situation. So we can find out what about the value of time taken for it. Now in this question it is given that the time t1 is nothing but the time taken to change the value of so we can write in terms of this, that is h minus root of h1, and like as we know that other things are constant, so t is directly proportional to this. So we can just write it as this t1 divided by t2. This t is directly proportional to this, so t1 by t2 is equal to initial height minus the value of final height divided by same thing, initial height minus final height. So if you are putting the value, so let's see what is given in question. In question it is given that 1/4 of the tank is emptied. So if 1/4 of the tank is emptied in time t1, that means we are assuming that initial height was something like h. Now 1/4 is emptied, that means 3/4 is left. So now the value of height is nothing but 3/4 times of h. So we can write 3/4 h. And in second situation, the time t2, it is given that the time remaining 3/4 of the tank is emptied in t2. So we can write in the second situation, we are assuming that initial height was something like h was nothing but 3h divided by 4, and final height h2 becomes equal to 0. So now we can put the value over here. The first situation, initial height was root of h minus h2 is nothing but a root of 3h divided by 4 divided by, in the initial situation the initial height was, or h1, h was something like 3h divided by 4 minus the value of final height which is going to be which is equal to nothing but 0. So we can find out what about the answer for it. So if you are going for cancel the value of h, root h, so we can cancel this root h, this root h, this root h over here. This remaining thing is 1 minus this is root 3 divided by root of 4, which we can take it as 2 divided by, this can be written as nothing but root 3 divided by 2. Now if I am taking this 2 as LCM, it is going to be 2 minus root 3 divided by 2, the whole divided by root 3 by 2. So this 2 and this 2 get cancelled, so we can write the answer as 2 minus root 3 divided by root 3. So that will be the value of ratio of t1 divided by t2.